Hi Year 7. So today we're going to be looking at the elements in Group 1 and Group 7. Now this is one of my favourite practicals to do, Group 1 elements. It's fantastic. You get to put lumps of metal in water and watch them explode. I love it. I really love it. They are less dense than water, so they zoom around on the top of the water, and in the case of potassium it catches on fire and it burns with a lovely lilac flame, and I love it. And I don't have any of these metals at home, and I'm absolutely gutted I can't make the video where I just blow stuff up. Hopefully you'll be able to do it next year when we're back at school, and if you want to watch it happening, I would really suggest you go to periodicvideos.com and watch the videos of their Group 1 elements, because they can do more elements than I can. So anyway, periodic table. Group 1 elements. My nice sort of maroony elements down here. We start off with lithium at the top. Okay? Now, as we know, because our good friend Dmitry Mendeleev told us, all of these have something in common. That's why they're in the same group. So what do they have in common? First of all, they react really, really well with water. They give off hydrogen gas, and as well as which they react with water to give off hydrogen gas, and they form an alkali. That's why they're called the alkali metals. So they form an alkali, whether it's lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and so on. Francium will not do much because it will decay radioactively. So you won't actually have francium by the time you get it ready to put it in the water. But all the others, lithium, sodium, potassium, rubidium, cesium, react with water. If you want to write down the equation for this, and this will be on the worksheet that you've got, it's lithium plus water makes, so you've got your arrow for makes, lithium hydroxide and hydrogen. Now we've already said that these all react in the same way. So sodium and water will make sodium hydroxide and hydrogen, and so on. But why do they react this way? Well, we need to go back to remembering what's in our atoms. Okay, so do you remember how we looked at the fact that we've got a lovely nucleus in the middle with positive protons and neutral neutrons, and zooming around on the outside, you've got electrons, negative electrons with no mass, and they're zooming around the outside of the nucleus. Okay. Oh. So what happens with these electrons is, because that's right, it's on. So what happens is you've got 2 electrons on the first shell, and the second shell you can have up to 8. But the second shell starts filling with lithium. The third shell starts filling with sodium. So each of these different periods indicate the start of a new electron shell. Yeah, and so what happens to the atom is that little electron zooming around on the outside, all the electrons sort of zooming around in the inside, inner shells, and that's fine. And then you've got this one little loner electron on the outside. And that little loner electron isn't very happy. It's going to zoom off somewhere else. And that's why these metals are so reactive. That little loner electron doesn't actually want to be there on its own. It does like the positivity of the nucleus, but it doesn't like the negativity, of all the other electrons. I think, go show that to Daddy. Yeah, I think that the negativity of the other electrons, I know this, don't think it, it stops it from being able to get near the positive nucleus, and that's why it's like, oh, you know what, I'm going to go off to another atom. So that's group 1. As I say, if you can watch periodicvideos.com of them blowing up lithium all the way down to cesium. It is well worth a watch. Okay, group 7 now. Our lovely sort of golden tanny colour over here. These ones are called the halogens. Now, this comes from the word gen, meaning makes. So hydrogen means makes water. Oxygen means makes acid. Unfortunately, those names are wrong. Oxygen doesn't make acid. Hydrogen does. Oh well. But in this case, halogen, they make salt. So we start up here with fluorine. Can you please note the spelling? Fluorine. It's not fluorine. However, having said that, even at GCSE, you won't get a mark knocked off for spelling it incorrectly. It's just a bit of a pet peeve. So we've got fluorine, chlorine, bromine, iodine, astatine, and when this periodic table came out, this was unnamed. I think it does have a name now. I can't remember what it is though. So what do all these have in common? They're in the same group. So that means they must all have something in common. How many of you guys have ever been swimming? Yeah? Do you know what a swimming pool smells like? That's pretty much what all the halogens smell like. You really don't want to smell fluorine, that will kill you. Chlorine, again, you get a lungful of that, you are going to die. This is the gas that they used in World War I and World War II to kill people. Okay? In World War I, it was blown across the trenches with the hope that it would kill people. The wind tended to then blow it back and it was killing some of their own men. So that got stopped. But it was used in the concentration camps to kill people in World War II. Bromine, from the Greek word bromos, meaning big smell. And that smells like a swimming pool, only about 1,000 times more. It's dreadful. Iodine, because it's a solid, you can't really smell it, but it does have, certainly if you've ever been for an operation and they've painted you with that brown substance around the wound to kill off all the bugs, that's iodine water, and that does smell a little bit swimming pooly. Astatine, its very name, astatos, I think it comes from, means unstable, and its radioactive half-life is tiny, so we don't actually know what it smells like, because if we make it, by the time we've been able to smell it, it's changed into something else. It is radioactive. So let's just look at these four. Again, periodicvideos.com have some great informational videos on them, but I just want to say, what do they have in common? We've got a yellow gas, a green gas, a reddish-brown liquid, and a grey solid, which will sublime, and that means it changes from a solid into a gas without being a liquid in the middle. It will sublime into a beautiful purple gas, and I love playing with that. It's fantastic. So they're all colourful. What else do they have in common? Fluorine is possibly one of the most deadly elements out there. Please note fluorine, not fluoride. Fluoride is safe. It's the stuff that's in toothpaste. Okay, fluorine isn't. Chlorine, we know it's a deadly gas. It's killed people. Bromine would be a killer if anyone could put up with the stink of it. And iodine is actually really essential. If you don't get it, it'll kill you. You need it in your thyroid glands, in your neck. But it does kill bugs, which is why it's painted on you before surgery. So the halogens are all killers. They're colourful, they are killers, and they all make salt. So if you were to react them with a metal, it would make a salt. And why does it do that? Well, we're going back to what the atom looks like. Okay, nice, big, positive nucleus. And then the electrons all zooming around. But in this case, we've not just got the inner electrons, the electrons on the outer shell are zooming around. This is where we start a new shell. That means that these ones the noble gases, have a full outer shell, because the next electron goes onto a new shell, which means these guys are only missing one electron. And that's why they're so reactive. Okay, what they like to do is grab an electron. It doesn't matter where from. And they really like to grab it from metals, because their electrons are, I'm not going to say going spare, but they're all on their own and they quite happily clear off to join with the halogens. So yeah, that's why they react. These guys are losing their one electron from the outside, and these guys want one electron, so they take it. Okay, the most famous example of a group 1 reacting with a group 7, if you can find a video on this, it's amazing. I love doing this one as well. Sodium reacting with chlorine, and that makes a very famous compound that you've probably heard of, sodium chloride. It's the stuff that you put on your chips. You know, back before this social distancing happened, I was down at the pub having a meal with my family, and this bloke, he threw some sodium chloride at me. I said, hey mate, that's a salt. Yeah, I'm full of great jokes. Okay, so what I'd like you to do today, obviously this has been a little bit of a dry video because I can't show you me exploding things, and I'm quite sad about that. You need to know how group 1 reacts, how group 7 reacts, why they do that, because of those outer shell electrons. You also need to know which ones are more reactive. Now, in case you're not going to go and watch somebody else's videos, good for you, I am a source of all knowledge, I'm all you need. The further away the electrons get from the nucleus, the less pull the nucleus has. So cesium is the most reactive on group 1. For group 7, that reverses. Fluorine can attract electrons because the electrons can get close to that nicely positive nucleus. So fluorine is the most reactive. When a metal reacts and loses an electron, it keeps the same name. Lithium, lithium, sodium, sodium. When group 7 reacts, when they gain an electron, they become a negative ion. We say ion instead of atom when it has a charge. So a fluorine atom becomes a negative fluoride ion. Chlorine becomes chloride. So that's why it's sodium chloride. Bromine, bromide, iodine, iodide, and so on. Okay? So fluorine's the most reactive and cesium's the most reactive. I do have a nice little worksheet for you, including a couple of little equations to do on what happens when group 1 and group 7 meet and react. So good luck with that, and I will see you for a new video very soon. Bye.